Francis, Francis, can you hear me?
Sir, good evening, sir. I can hear you.
Francis sir, hello. Francis sir, you are muted. Am I audible, sir?
Sir,
Sir, am I audible?
yes, sir, you are audible.
Yes, sir. So
Right. Sir,
can
one minute.
can you allow
Sir,
me to start the
once,
video and share the screen?
yes, sir.
Is my screen visible, sir?
Yes, sir, visible, sir,
Okay.
but partly visible.
Yes, sir,
Yeah,
visible.
yeah. I have to go
Maybe,
to the screen share mode, right?
yes,
Slide,
sir.
okay. Slideshow mode. I will share. Now it is visible fully.
Yes, sir.
For
Yes, sir,
few
is it now completely visible?
okay. For few
1
minutes,
second, sir.
you can allow me to start my video for few minutes.
Yes, sir, yes. Sir, we will start in
Yes,
another
sir.
2 minutes, sir.
Sir, I cannot start my video. Can you permit me?
Yes, sir. From my side, I'll give.
Yes.
Sir, I made you host.
Yeah, yes. Now it is fine, sir. Is my video visible?
Yes, sir, yes, sir.
Yes, sir. We can start, sir. Yes.
So, very good evening to one and all present here. An investment in knowledge pays the best interest. With a quote by Benjamin Franklin, I, Dr. Francis Luther King, Associate Professor from Department of Mechanical Engineering, coordinator for this 6-day online FDP on recent advancements in materials manufacturing and technology. And my co-coordinator, Dr. R. Associate Professor, Mechanical Engineering Department. I now invite Dr. Robert, Professor, Mechanical Engineering Department, to give a welcome.
Good evening, one and all. Dr. Robert, Professor, Department of Mechanical Engineering. It's a pleasure to welcome you all for this 1 week faculty development program on recent advances in materials manufacturing and technology. So, on behalf of our college management, convener, principal, and the organizing committee, I would like to welcome you all. And I would like to welcome our resource persons. Today, first session, resource person, Dr. Mohammed Iqbal, Professor, Department of Mechanical Engineering, SRM University, Kattankulathur, Chennai. And I would like to welcome Dr. Arul Jeyakumar, Professor, Department of Mechanical Engineering, SRM University, Kattankulathur, Chennai. So, welcome you. Once again, I welcome you all. Please keep your mics on mute conditions for better audio quality, please. And Dr. Francis.
Thank you, sir. Thank you for your welcome. And I now introduce our today's resource person for the first session, Dr. Mohammed Iqbal, Professor, Department of Mechanical Sir has completed his PhD from College of Engineering, Guindy, Anna University, Chennai, having 25 years of experience with research interest in the area of metal forming, metal joining, mechanical metallurgy, composite and nanomaterials, severe plastic deformation, optimization techniques. And Sir has handled various courses, to mention a few, like mechanical behavior of materials, global optimization algorithms, fluid power control, etc. Sir is having supervisor recognition from various universities and a PhD supervisor in Department of Mechanical Engineering, College of Engineering, Guindy Campus, Anna University, and recognized PhD supervisor in SRM University, and PhD Associate Supervisor in the Department of Mechanical Engineering, Curtin University, Australia, Malaysia campus. And Sir has guided 3 PhD students and currently guiding 5 PhD students. And Sir has been appointed as various doctoral committee member in various universities like Anna University, Veltech, Rangarajan, Dr. Shakuntala R&D Institute of Technology, Avadi, Chennai, and Hindustan Institute of Technology and Science, Chennai. And Sir has editorial achievements in various journals, international journals, and reviewer in Journal of Material Processing Technology, Materials Today, Silicon, SN Applied Sciences, Journal of Polymer and Environment, and so. And Sir is having some achievements, guest editor, Sir.
Yes, your voice is not audible. You have finished.
Yes, sir. Yes, sir.
Yeah. Thank you, Dr. Francis, for your nice introduction, and also I thank you for
welcome, sir.
Yeah, I thank you for adding me as a resource person in your recent advancement in materials manufacturing technology, that is 1 week online FDP. So good evening, friends. Good evening, faculty members. So today I'm going to give a lecture for 1 hour. Okay, I think the 1 hour is not sufficient for me to complete this broad topic. Anyhow, I'll try to maximize as early as possible to complete my topic. So I'm going to give a lecture on advances in metal forming research, a comprehensive review. So my area of research, already Dr. Francis told, my area of research is severe plastic deformation, mainly metal forming techniques, and also machining, optimization studies, and composite materials. So today I'm going to give a brief research review on advances in metal forming research, especially in a severe plastic deformation, which is my area of research. So now I will stop my video because of better audio quality, right? Right. Next. So you all know metal forming includes a large group of manufacturing process in which the plastic deformation is used to change the shape of the metal workpiece. You know what is a plastic deformation? It is a permanent deformation. After the elastic limit, the material will deform plastically. That is, the strain is permanent. Okay, which where the equation sigma is equal to k epsilon power n is governing equation at that state, whereas in elastic region sigma is equal to E epsilon, where modulus of elasticity comes into picture, which obeys Hooke's law in the elastic region. So the material deforms plastically, okay, in the metal forming process, where the deformation is permanent. So large deformation results from the use of a tool, usually a die in a metal forming process. So die is the main component in the metal forming process, which applies stresses which exceeds the yield strength of the material. So material will deform plastically once it exceeds the yield strength of the material. Right. So metal forming process can be classified into two major areas: sheet metal forming and bulk deformation. So sheet metal forming is also called as a press working. It is generally a cold working process which uses a set of punch and the die, which is performed mostly on metal sheets, strips, and coils, where the surface area and the volume is large in a sheet metal forming. This is a broad area, so I'm not going to touch upon the sheet metal forming because my area of research is in bulk deformation. So bulk deformation is a deformation where a compressive deformation force is predominant, where a significant deformation occurs in the material, where massive shape changes are enabled, where the starting workpieces include billets and rectangular bars, where the surface area is very, very small when compared to the sheet metal forming. So mostly the raw materials which is coming out from the industries okay, are subjected to bulk deformation, where we are increasing the strength of the material by deforming it, to reduce the grain sizes so that the strength is increased. So this is the process why the surface area and the volume is small in the bulk deformation process. Now, if you go to the grain sizes plays a major role on the deformation. So whenever we are reducing the size to nano size or the ultra fine grain size, the material strength gets improved. So these are the various grain sizes obtained by various cooling methods. So if you slowly cool the metal, that is mostly the annealing process, we get a single crystal where the grain size is coarse in the range of several millimeter to centimeter. If you go for a sand casting technique where the cooling rate is somewhat medium, where we obtain a coarse medium grain strain structure, the grain size will be in the range of 200 to 50 micron meter. If you go for a die casting, the fine grain structure, medium fine grain structure are obtained in the range of 50 to 110 micron meter grain size. And if you are cooling it fast, we get a finer grain size, the ranging from 5 micron meter. Microalloyed steel, that is, if you are microalloying it, we are adding some nano ingredients like niobium, vanadium, and titanium. I think you have been aware of TMT, thermomechanical treated bars. Nowadays, commonly we are using for construction purpose. So they are called as mostly microalloyed steels. So they produce a very fine grain structures in the range of 1 micron meter. So nowadays people are working towards a new severe plastic deformation techniques, which produce an ultra fine grain structures where the grain size is less than 1 micron meter. So what is an ultra fine grain structure? So ultra fine microstructure is obtained by extremely large plastic deformation. That is, intensive plastic deformation is enhanced in the die itself. Such deformation can be imposed by special deformation techniques which are called as SPD techniques nowadays. So they are capable of producing polycrystalline structures with the grain size in the order of 100 nanometers or even less. So actually this process, SPD process, we call it as a top-down approach. Okay, there are two methods of processing the materials in metal forming. One is the bottom-up approach, where we are consolidating the material from powder to a bulk stage. Okay, then we are obtaining the nano size grain structure. So in the top-down approach, we will have the bulk material. Then we will process it through various metal forming techniques. Mostly the material is severely deformed in a die. Okay, so that the material grain size is refined. So this is called as a top-down approach. So SPD process is mostly it's a top-down approach for processing of a nano structured materials. Severe plastic deformation means an imposition of a large extreme plastic chain on sample that does not result in significant change in the sample's geometry. You have to note this point, does not result in significant change. Okay, this is very important in a severe plastic deformation. So whenever we are extruding a sample, okay, you know what is an extrusion? Extrusion, a process of passing the material through a confined opening, so that the initial size, initial diameter will be reduced, and the final diameter will be small when compared to the initial diameter, where the extrusion ratio does not remains constant. Whereas in the severe plastic deformation, the extrusion ratio will be remaining constant. The component which you are passing through the larger diameter will commit in the same diameter even after inducing a severe plastic deformation. So I think some disturbance is occurring. Someone is not muted. Okay, I'm getting the disturbance. Please check that one. From the participant side, kindly unmute. Sorry, kindly mute. Okay, I think still the disturbance is coming. Okay, so the micro refinement by SPD is based on general trend. What happens when we are deforming severely inside a die? Okay, it forms dislocation substructures which consist of subgrains. Okay, so large number of grains. Okay, due to the dislocation, the material, if you are resisting the motion to dislocation, okay, so the strength of the material increases, which creates a substructure. Okay, substructure and subgrains, so that due to more plastic strains, okay, the material becomes severely plastic deform, and we will get a ultra fine grain structure. This is the concept of this process. According to Hall-Petch equation, you know what is in the Hall-Petch equation? Okay, it gives a relationship between yield strength and the diameter of the material. Yield is sigma y is equal to sigma naught plus kd power minus half. Okay, that is the equation. So the yield strength is directly proportional, inversely proportional to the diameter of the grain size. So the strength of the material is inversely proportional to the square root of the grain size. So mechanical properties depends on its grain size. So fine grain in the metal can be developed by two approaches, as I told already. One is by powder metallurgy, one is by top-down approach. That is, powder metallurgy is a bottom-up approach where we are consolidating the powder materials to a bulk material. Okay, whereas in the top-down approach, we are reducing the size of the grains of a bulk material to a nano size or ultra fine grain size. So severe plastic deformation is one of the top-down approach, right? So when you are seeing this diagram, you can see this large area of severe plastic deformation techniques and their derivative process. So if you see the basic SPD process, equal channel angular pressing, accumulative roll bonding, high pressure torsion, multidirectional forging, and twist extrusion are the common SPD process. Okay, so all other are derivative process, or the combination of these two process or three process like that. Okay, people are working nowadays in the research area. So these are the older techniques. Okay, whenever when the SPD process evolved out, these five techniques are the most common basic techniques. So some derivative techniques are derived from these basic SPD techniques, like repetitive side extrusion and so on. You can see this one, right? So now we are focusing on the basic SPD techniques with respect to some research works, right? So I'm going to focus on 5 different SPD techniques: high pressure torsion, accumulative roll bonding, equal channel angular pressing, twist extrusion, and twist channel angular extrusion process. You can see the high pressure torsion process. This is the actually high pressure torsion process. It is the technique in which a disc-shaped sample is rotated between two anvils. Okay, you can see these are the two anvils. A disc-shaped sample is rotated between these two samples. So the number of rotations and the pressure are the two parameters which governs the grain size of this material. Okay, so more number of rotations and high pressure will lead to finer grain size and homogeneous grain size structures. Okay, so rotation of one of the anvils forces the sample to deform by torsion. So up to 5 rotations of the anvil are usually enough to form a homogeneous microstructure with the grain size. Actually, the grain size achieved by this process 100 nanometer to 50 nanometer. So this method can enable us to produce the samples with a diameter of 20 mm and thickness about 0.2 mm. This is the basic principle behind high pressure torsion process. You can see one case study. So this is the effect of you can see the effect of pressure on grain size in HPT of GH4169 alloy. Okay, so GH alloy is a super alloy, okay, which is mostly used for processing turbine blades, etc. Okay, turbine blades. It's actually a precipitation hardened nickel based super alloy, which is used for producing aircraft engine engine discs, rotor components, compressor discs, etc. Mostly this GH461 alloy is mainly processed by this process. Okay, that is high pressure torsion process. You can see these 3 different microstructure. Okay, the 3 different microstructure are produced by pressing the samples at different pressures and different number of cycles. You can see the microstructure of annealed sample at different pressure. That is the first microstructure is 3 gigapascal pressure is applied with the 2 number of passes. Okay, you can see the grains are severely broken with 3 gigapascal and 2 number of passes. You can see the shape of fracture. The shape of this grain is a needle-like shape was fractured into a irregular shape with various sizes. You can see different sizes of the grains. Okay, so on applying more pressure, okay, and the same number of cycles, you can see the grains are severely crushed again. Okay, when the pressure reaches the 5 megapascal, okay, you can see the grains are oriented in the same direction and the homogeneity is attained. Okay, homogeneity is attained and the grain size gets decreased. Okay, this is how the high pressure torsion produces an ultra fine grain structure with more pressure and more number of passes. Then this is the effect of the Vickers hardness. The hardness is measured on the radial coordinate of the samples, which is processed with the 5 gigapascal and 2 number of passes, 4 gigapascal and 3 gigapascal, and the original sample. You can see this original sample. This is black in color. So the hardness of the original sample is 250 to in the range of 250 to 260 Vickers hardness. Okay, so whereas if you see the material process with the 5 gigapascal and the 2 number of passes, you can see the difference in the hardness. Okay, it is almost the homogeneity is achieved in the hardness. So we can see that almost the line is straight. Okay, so we can attain a hardness value of 310 when compared to 250. Okay, which is the original sample. Okay, so hardness also increases. That is the beauty of SPD techniques. The hardness also increases. The strength also increases. Right. Coming to the next process, accumulative roll bonding process. So accumulative roll bonding is nothing but similar to a composite process. Okay, in composite, what we are doing is we are straddling one metal over the other by applying some coupling agents and additives in between them. Okay, like that, what we are doing is first we have to prepare the sample. That is very important in this process. Okay, first the sample is cut to the required dimensions. Okay, and we have to remove all the greases and the dirt particles which is present in between the surfaces. Okay, then we have to apply the coupling agents in between. Okay, then it is tied with some steel wires. Then it is passed between 2 rollers. Okay, you can 2 rollers. Initially, the size thickness of the material, 2 layer of material is 2T. Then it is passed through the rollers. Okay, you can see the thickness reduced to T. Like that, we can develop many number of materials. Okay, so you can see as the number of rolling passes increases, the material is subjected to severe plastic deformation. Thereby, the grain structures are getting homogeneized and it is getting reduced. Okay, so you can see the effect of this ARB on the texture and tensile properties of magnesium alloy produced by this ARB process. Okay, so you can see this is the EBSD sample. Okay, so you can see the EBSD microstructure of the samples. This is the as received sample. The second one is the sample after one pass. This is the third pass. Okay, you can see initially the initial microstructure, okay, has size of 100 micrometer. Okay, that is the large grain size. 100 micrometer dominate the microstructure, and also see the grains are oriented in different direction. Okay, the orientation of the grain size you can see in this one. You can see the color mapping. Okay, so the blue color is oriented in 1010 direction, and the red color mapping is oriented in 0001 direction, and the green color is mapped in 1120 direction. If you have to note one point here, the Miller indices is designated with 4 numbers in case of magnesium alloy when compared to other materials. Okay, because it is a hexagonally close packed structure. Okay, since it is an HCP structure, the Miller indices are designated at the 4. Yes. Any doubt? Do you want to ask anything? So am I audible? Nobody's participants?
Yes, sir. Yes, sir.
Audible, sir.
Okay. Thank you. Right. So you can see these are the orientation of the grain size. I can see this 1010 is dominated by the blue color, and 0001 is dominated by the red color, and 113020 is oriented by the green color. Okay, in the initial sample. Okay, so once the accumulated roll bonding, the first pass of the ARB process, you can see the grains are oriented in a different direction, and the high angle grain boundaries are reduced to the low angle grain boundaries. Okay. Now, when you go for more number of passes, with the 2 number of passes, you can see the grain structure is reduced to 10 micron from 100 micron meter. Okay, the average grain size is reduced from 100 micron meter, 10 micron meter, and it is mostly dominated by the red color structure, that is 0001 structure. So it indicates that the sample is homogeneously, that is the homogeneity of the grain size in the sample is ensured. Okay, of more number of passes. With the EBSD samples, we can see this one. Okay, now we can see this is the that is the effect of true stress with the number of passes with A is at 31 processed at various temperature. So temperature is also having some influence on the microstructure. Okay, microstructure and the stress, tensile stress. You can see at 23 degrees centigrade, the material is cut into, that is the tensile stress values is calculated by taking the samples between the transverse direction and the lateral direction. You can see RD is the lateral direction and TD is the transverse direction. Okay, you can see the with 0 number of passes. Okay, you can see the ultimate tensile strength of lateral direction sample. Okay, is more when compared to the other samples. That is the transverse direction, the lateral. That is the tensile yield strength of. This is the tensile yield strength of the lateral sample. This is the tensile yield strength of the transverse sample. Similarly, the ultimate tensile strength of the lateral sample and ultimate tensile strength of the transverse sample. You can see like that. It's the number of passes increases. Okay, at 23 degrees centigrade, when the number of passes increases, you can see the higher temperature is achieved for the sample which is taken in the transverse direction. Okay, so a small difference between 1 and 2. Okay, not much difference is obtained. At 100 degrees centigrade, you can see there is a reverse effect. Okay, so the samples which is processed, the tensile stress of the samples with ultimate tensile strength, the ultimate tensile strength of the transverse direction sample gets reduced at high number of passes when compared to the first 1 number of passes. Okay, so this has a different effect. Okay, this is the sample process at 200 degrees centigrade. You can see there is another similar to the previous one. We have a dominating the tensile strength for the 0 number of passes. Okay, so and the same trend is obtained for 300 degrees centigrade. So the tensile yield strength is smaller, and the highest temperature of 300 degrees centigrade. Okay, the yield strength of the samples with different orientation are comparable. You can see the tensile strength is more at 300 degree centigrade when compared to this one. Okay, right. So the next one is next process, equal channel angular processing process. Okay, you know what is an equal channel angular processing process? That is here in these processes. In the previous process, the number of passes has to be increased again and again. We have to take the sample after 1 number of passes. We have to once again pass the sample to another pass. Okay, pass in between the 2 rollers for getting the another pass. Okay, so in order to reduce that one, equal channel angular processing process has been developed. Okay, in which they have increased the deformation zones. Okay, already there is one deformation zones. Okay, one deformation zone here. Okay, it is coming out by this one. So there are commonly 2 methods, 2 methods of ECAP. One is this angle, that is deformation angle will be 90 degree and the deformation angle will be 135 degrees. This is the common angles which researchers are worked on. Okay, so the ECAP utilizes a die containing two channels of equal cross section intersecting at an angle of 2 theta or 2 phi, which normally varies in the range of 90 to 135 degree. Okay, on passing this two channel, a sample maintains the shape except for small portions at the ends. You can see. Okay, so after one pass, the sample is being passed through the same die. Okay, but rotating the sample in several directions. We can see that one here. Actually, this is the actual die of ECAP die with a 90 degree angle, channel angle. Okay, so you can see the grain size which is produced with the material. Okay, you can see the dimensions of this sample is regaining in this process. That is the beauty of SPD techniques, ECAP process. Okay, whatever the dimensions you are passing, okay, the material is severely deformed here. When coming out, comes with the same shape and size. Okay, so that we no need to bother on the extrusion ratio. Okay, the extrusion ratio remains 1 in this process. Okay, and we have only one deformation zone. Okay, so in order to attain the homogeneous grain refinement, what the people are doing is first they are passing the sample through this process. Okay, first they are taking this sample and they are passing the same sample and the same direction in the first pass. It is called as route A. Okay, so in the route BA, you can see the first they are taking it, the sample, and they are rotating it to positive 90 degree and they are processing for the second pass. Okay, and the third pass, they are rotating it to minus 90 degree and they are going for third pass. So that is route BA. And the third sample, you can see the process, the component is processed after first pass. They are rotating it to only 190 degree, positive 90 degree, and they are processing the sample. And the fourth pass, that is called as route BC, and the fourth sample, they are rotating it to 180 degree and they are passing it for the second pass. So by doing this, there is a large lot of effect in the homogeneity of the sample and the grain refinement. Okay, that is what these people, Venkatachalam et al., who carried out the work in 2010 has reported. Okay, these are the 10 images of 2014 aluminum alloy for different processing route. You can see the route, the material processed by, okay, that is route BC. Okay, BC is nothing but only plus 90 degree. Okay, has reasonably equiaxed grains when compared to the other structure. Okay, the average grain size of 0.15 micrometer after 5 ECAP passes is attained in BC. Okay, according to the results. Okay, so this is the effect of number of passes on mechanical properties. You can see as the number of passes increases, the hardness value increases. Similarly, the tensile strength values increases for 4 pass ECAP sample when compared to the parent metal. You can see this is the parent metal. Okay, so the parent metal ductility is more. Okay, the ductility is reduced for the other materials processed by 1 pass, 2 pass, 3 pass, but the strength is improved. Okay, you can see the strength of the material gets improved. Okay, after 4 number of passes, it is in the range of 450 megapascal. So next process is a twist extrusion process. This is actually my PhD work in which I have did my PhD. So people have worked with one deformation zone. Okay, so then require the sample to be processed to several passes to attain the ultra fine grain structure. So they need to go for 4 or 5 number of passes. So I thought, why can't we develop induce one more deformation zones? Okay, why can't we induce one more deformation zones, or why can't we make a different design? Okay, so I have made a twist extrusion process. That is, instead of rotating only to 90 degree, I have rotated the sample a slope angle. Okay, I have given a slope angle beta and a twist angle 90 degree. Okay, so this is the, see, the component is passed through this one and it is completely twisted to 180 degree when it is coming out. Okay, so when you are passing it to the width side, it is coming out the thickness side. Okay, so like this, so more deformation is induced inside the sample. Okay, so the number of passes can be reduced by doing this process. By see, you can see the equivalent plastic strain also achieved. The sample, whenever it passes through the initially, the same dimensions is achieved in the component which is coming out. Okay, the shape and dimensions of the workpiece do not change. Okay, you can see these are the angles. Okay, so these are the beta. Here the slope angle, the change in the slope angle and the twist angle is 90 degree. Twist angle is maintained 90 degree and the slope angle of beta is given a 60 degree for enhancing the component to rotate and come out of the die. Okay, so alpha is the twist angle 90 degree and beta is the slope angle 60 degree. Okay, so these are the effect of twist extrusion on the properties of 6061 T6 aluminum alloy. Okay, you can see the material processed by different temperatures. Okay, have different effects on the material. So more number of passes, that is at 500 degrees centigrade, and more number of passes, that is 3 number of passes. The material has high hardness, at the same time the high tensile strength. That is the result of this research work. Okay, so you can see the grain structures, optical micrograph and the same microstructure of the 6061 T6 before extrusion. Before extrusion, you can see the equiaxed grain structures with a lot of twins present in the sample. Okay, so the grain size is more than 30 micron, 30 to 40 micron size. Okay, so after the material is processed with the twist extrusion, you can see the sample size, the grain size is reduced. Okay, you can see large number of low angle grain boundaries. Okay, more number of low angle grain boundaries at 500 degrees centigrade, that is E to F, the material processed after 500 degrees centigrade, so that the material strength is improved. Okay, at the same time, the hardness of the sample also increased. So these are the simulation results of the contours of the twist extrusion sample after the die is being manufactured. Before conducting the experiment, the simulation is carried out whether the die is suitable for extrusion process. So we have carried out various simulations, and finally we succeeded with the sample. Okay, succeeded that the process can extrude the sample. After doing the FEA simulation, we have carried out the experiments and conducted the experiment successfully. Right. This is the another study which has an effect of number of passes and processing route in a twist extrusion of the pure copper. Okay, you can see the hardness. Why they are taking the hardness value at distance from the different end means because in order to check the homogeneity. Okay, so you can see at the annealed sample. This is the annealed sample. Okay, you can see at one number of 1 mm. Okay, from the edge. Okay, 1 mm from the edge. The hardness is more. Okay, when hardness is more, as it goes on, the hardness increase. Okay, at 5 mm. Right. So if you go for one pass twist extrusion sample, you can see the hardness is increased. Okay, it goes on decrease from the distance. So it infers that the inference of this one, the hardness is more at the edge when going towards the center of the samples. So what to do? How to increase the hardness of this sample? Okay, the people started working on this one. Okay, because the homogeneity will not be same. Okay, if the hardness values differ from the edge to the center of the sample, the homogeneity will not be the same. Okay, so we have to process in different routes. Okay, the component should be either we have to go for different number of passes or more number of passes. Okay, that is one of the drawback of the twist extrusion process. So you can see, I'll come back to the other process, how the homogeneity is increased. You can see these are the color mappings obtained after the twist extrusion. After 2 passes twist extrusion, you can see initially the initial grain structure is coarse, which is dominated by different structures, different color maps. Okay, and the grains are oriented in different direction, 111, 001, and 101 direction. Okay, and you can see this is the next after processing with another. Okay, so orientation color grain boundary map is center of the samples after 2 passes. This is the center of grain boundary map of surface of the sample. This is taken at the surface. This is taken at the center of the samples. Okay, these two diagram which gives the difference between the color mapping, EBSD mapping taken between the surface and the center of the samples. You can see at the there is a difference in the edge and the difference in the center of the samples. So there is no homogeneity in the grains which is processed by twist extrusion. That is the drawback of the twist extrusion process. So the people started to go for another process called as twist channel angular processing process, where they have imposed another deformation zone. That is, they have combined the twist channel twist extrusion along with the ECAP process, because already there is one slope angle and twist angle is there, and they are inducing one more corner angle. Okay, corner angle, that is 90 degree or 135 degree, so that the number of passes can be reduced, so that the material is deformed twice. Okay, before it is coming out of the sample. Okay, so that the deformation is more with one pass. At the same time, the homogeneity is more. Okay, that is the outcome of this result. In the first part of the channel, there is a twist with a slope angle of 50 degree, and it is followed by bending of channel at an angle of 90 degree here. Okay. So in comparison with this, already I told this one. So maximum imposed strain achieved by the authors of pitch to channel angular pressing was 2.3, and still there is a scope for increasing it. Okay, right? You can see this the comparison of hardness of the copper alloy processed by ECAP and TCAP process. So in the ECAP process, you can see these are the ECAP processed samples. Okay, this is undeformed samples where the micro hardness is in the range of 40. And ECAP 1 pass, it increases to 60, and ECAP 2 passes increases to 70. But you can see the TCAP process samples, that is these two, green and blue color. You can see the TCAP process samples have higher hardness when compared to the ECAP process samples. So it shows clearly that inducing more deformation zones increases the hardness and strength of the material. Okay, you can see this is the comparison of strength of the copper alloy. Okay, the strength of TCAP processed material is high when compared to the ECAP passes. Okay, the more number of passes induces more strength and more hardness. Okay. Right, these are the microstructure of the samples processed prior to TCAP and after TCAP. You can see the coarse grain structures is obtained. Okay, in the TCAP, which has less strength. You can see the material processed after TCAP. We have finer grain structures and large number of low angle grain boundaries. Okay, and you can say you can see that the material is refined, which improves the strength. At the same time, the hardness of the material is improved. Okay, so coming to the recent research aspects in SPD process. So people are nowadays working with a secondary process after SPD of metals. Okay, like they are also started to process the bimetallic metals. Okay, then what happens when we are aging the material after a severe plastic deformation? Okay, and they have developed a new novel integrated SPD techniques. Okay, so we'll quickly go into see, because running out of time, only 20 minutes more. Before 10 minutes, I have to stop for asking questions. So quickly I will run. Performing secondary process after SPD of metals. So the people have started working the ECAP plus annealing and cold rolling. So in ECAP, after processing the material with ECAP process, then to enhance the properties of the material, they gone for annealing and the cold rolling. Okay, ECAP followed by annealing, ECAP followed by cold rolling process. Okay, you can see to achieve the strength and elongation of AA1014 alloy through ECAP, intermediate annealing and post rolling at room temperature. Okay, so the ECAP process was carried out on the annealed sample, and none of the sample has rotated during entire ECAP process. First, they have processed the sample on ECAP without rotating. Okay, without rotating the samples either to plus 90 or minus 90, whatever the direction they have, the component is coming, the same direction they have passed. Then the samples were annealed into two different temperatures, 150 and 225 degrees centigrade for 1 hour to investigate the effect of the intermediate annealing on the temperature and microstructure. And the specimen were cold rolled. After annealing, they have cold rolled until 50 to 75% thickness reduction to study the effect of cold rolling. This is the work carried out by Ahmadian et al. In 2022. Okay, you can see these are the results they have obtained. So code of specimen, number of ECAP passes, the S1, S2, they have given code of 16 samples. Okay, so number of 1 ECAP pass with intermediate annealing of 150, 225, and 150 and 225 degrees. So sample 2 with 1 number of passes, 225 degree, 225 annealing temperature and rolling percentage reduction 50. They have used 50% reduction, 75% reduction. They have used 150 degrees centigrade and 225 degrees centigrade, the annealing temperature, and they have gone for 4 number of passes. Okay, so you can see these are the effects. Okay, the effect of strain path, intermediate annealing, post rolling process, microstructure of the samples. So first specimen with the 2 passes ECAP plus annealing, you can see the grains are elongated along the direction of ECAP. Okay, so with the 4 pass ECAP, you can see the grain sizes are reduced. Okay, the coarse grain structures are reduced to fine grain structures. Okay, with 4 pass and annealing, you can see the homogeneity is achieved. Okay, after annealing, you can see the homogeneity, you can see the color mapping. So here a lot of green color is dominated. Okay, but you can see in this 4 pass ECAP plus annealing. Okay, so it is homogeneously mixed. This green color, more green color is being homogeneous mixed, and further rolling of this one, you can see this is dominated by the structure that is 1-1-1 direction. Okay, so they're dominated by 1-1 direction. That is the center of the sample, edge of the sample, corner of the sample are dominated by 1-1-1 orientation. Okay, so the grains are oriented in a particular direction after annealing and rolling, so that the homogeneity of the sample is maintained. At the same time, the strength and improvement in the hardness values are achieved. Okay, so after 5 number of passes, you can see this is a 4 number of passes. Okay, right. So these are the explanation what I have already given. The effect of ECAP intermediate annealing, you can see for the sample 1, sample 2, sample 3, and sample 4 and sample 5. Sample 5, you can see the sample 5, okay, which is annealing and rolling. Okay, more passes of rolling. You can see the sample 5 has very good results. Okay, at the homogeneity of the sample is maintained. Okay, you can see the homogeneity is different. You can see the effect of number fraction. That is number fraction versus misorientation angle. Misorientation angle. What is orientation angle means? So the grains are oriented in several directions. You can see this one. Here, the orientation of the sample is along a particular direction. Okay, that is what the inference obtained from this work. Okay. Next. So next, processing of bimetallic metals. Okay, so the twist, they have taken the twist extrusion as a SPD process for production of aluminum and copper bimetallic bar. Okay, so how they have prepared the material is, you can see they have made a hole in the copper material. Okay, they have induced the aluminum rods inside the copper material. Okay, so first they have did this one, right? They have inserted the aluminum material inside the copper tubes. Okay, copper tubes, and they have prepared the material. Then they have made the material to pass through the twist extrusion process. Okay, so where it is, the material is twisted at the slope angle of 37 degree and the twist angle of 90 degree. Okay, so they produce bimetallic bars under the following modes. Only forward extrusion first, then one twist extrusion pass followed by forward extrusion, then 2 extrusion pass followed by forward extrusion, and 4 extrusion passes followed by the forward extrusion. Okay, so in addition to twist extrusion, they have extruded once again with the forward extrusion process in order to regain the homogeneous condition of the material. Okay, so you can see the effect what happens, right? So this is the stress strain diagram. Okay, the blue color is the annealed sample. You can see the strength of the annealed sample is less when compared to the bimetallic sample processed with 4 pass twist extrusion plus 1 forward extrusion process. You can see the strength ranges from 300 to 350 degrees centigrade. Okay, then it goes on decreasing. Okay, from the center to end. Okay, the strain. This is the strain. You can see the strain. Okay, of the samples. So this is a viscous hardness. Similar trend, whatever we have noticed in this is being obtained in the separately. You can see the copper and aluminum. As annealed copper and aluminum, they have taken the hardness separately for aluminum and copper. Okay. Then after the bimetallic strip is produced, they have compared this one. So as annealed, copper produces a hardness of 68.8 with aluminum 49.5. The bimetallic sample with only forward extrusion, they have see the increase in the hardness of 79.6 for copper and 60.9 of aluminum. Okay, so then one pass twist extrusion plus forward extrusion, the hardness was increased from 79 to 94. Similarly, 94 to 105 with the more number of passes, and to 121.81 for 4 passes with the copper and 84.1 for aluminum. Right. So these are the microstructures. You can see the microstructure. Okay, the fine grain microstructure is obtained after 4 pass and with 4 pass twist extrusion and 1 forward extrusion mode. Okay, the grains are homogeneously distributed and mixed. Okay, so which induces high strength and homogeneity in the sample. So these are the optical microstructure. Still, you can get a lot of idea. You can see the coarse grain structure with the large angle grain boundaries. Okay, then after twist extrusion pass, you can see the orientation of the grains in the direction of the twist. Okay, so further twist and direct extrusion or twist extrusion, you can see it is the grains are oriented in the several directions. Still, the grains are large in size. Okay, after more number of passes and the forward extrusion process, you can see the grains are homogeneously distributed throughout the corner to the center of the samples. Right. So aging treatment. What is the effect of aging treatments of SPD of metals? So after aging, what aging means, we have to keep the sample in a position, okay, at room temperature for a long period of time. Okay, this study focuses on structural changes of a commercially pure aluminum process, in which they have selected a TCAP process, and they have kept the material after TCAP. They have kept 1 year and 2 years of natural aging at room temperature. Okay, then they have studied the effect of the samples which is aged for 1 year and which is aged for 2 years. Okay, 3 billets of commercially pure aluminum is processed through a TCAP process, single pass TCAP. 1 billet was processed by a single pass ECAP process. Okay, so out of the TCAP one, the first billet was examined right after processing, and the second one after 1 year of natural aging, and the third one was aged for 2 years. Okay, so they have found out the effect. What is the effect? They have found it. This is you can see the frequency percentage and the grain size. Okay, frequency percentage, this is the effect of the frequency percentage versus grain size. The grain size distribution after a single pass ECAP. This one is first diagram. Second diagram is the grain size distribution of a single pass TCAP process. Okay, you can see the grain size distribution of after TCAP and 2 years aged. Okay, you can see the 2 years age sample, the grain size goes on decreasing. Okay, you can see the grain size is very, very fine after 2 years aging. And E, it is a recrystallized fraction, but the diagram is not here. Okay, so, so this is a D, recrystallized fraction for 2 years aged TCAP sample. After recrystallization, you can see the grain sizes are oriented. Okay, this is the effect of aging. So if we are aging the material, SPD process material for a long time, still we can refine the grain size. That is, grains are recrystallized. Okay, after 2 years aging, which improves the strength of the material. Okay, you can see these are the 10 images taken from sample TCAP after processing, 1 year age, 1 year age TCAP and 2 year age TCAP process. Okay, right. So the electrical resistivity of the TCAP sample, they have found out the electrical resistivity. Okay, as the electrical resistivity decreases, the conductivity increases. Okay, so electricity, you can see after single pass, the electric resistivity is 2.707. Okay, so 1 year 2.720 and one. See, you can see the 2 year age process have the electrical resistivity of 2.65 into 10 power 5. Okay, which induces that as the electrical resistivity decreases, the conductivity of the sample increases. Okay, so this is the inference from this one. And now this is the technique, that is the novel integrated SPD technique. This is one of the technique I have developed along with my PhD student, and we have obtained a fund, okay, from DST, SERB, for carrying out this research, a novel SPD technique to process magnesium gadolinium alloy. Okay, the magnesium gadolinium alloy, right? So what we have did is, so already I have worked with twist extrusion. Okay, and before starting this experiment, I have carried out some experiments with the TCAP also. Okay, at that time I have gone through several finite element simulations, and we have optimized the die angles. Okay, we have optimized the die angles with that basic knowledge, and I have published a paper with this TCAP process in Material Research Express in 2019. Okay, after having this idea, when my PhD student joined along with me, we together developed this process, multi-angular twist channel extrusion process, and we have patented this die. Okay, it is waiting for the grant. We can see what is the process is here. Need for the made processes. We seen already the ECAP process, TCAP process. In the ECAP process, only one deformation zone. Twist extrusion process, we have 2 deformation zone. Okay, TCAP process, we have induced more deformation zone. Okay, but still the grain refinement and the homogeneity is less. That is the research reported. Okay, so from this, we taken this as a research gap. Okay, so why can't we impose one more deformation zone to attain a grain refinement of the sample without going for 3 or 4 number of within one pass? How can we attain the grain homogeneity and the grain homogeneity and also the grain refinement? So this idea has paved a way for in developing a made process. The amount of grain refinement achieved is limited into section ECAP and accumulated roll bonding. So in order to reach out the desired grain size, the material has to undergo several number of passes. This is one of the reasons why these processes are not commercialized. So this is a scope for novel techniques that can result in ultra fine in a single pass. So owing to this factor, a novel mate process is proposed to improve the properties. You can see this is what we have did. Okay, so this is a twist zone where we have a slope angle of beta and twist angle of psi. Okay, and we have imposed another angle. Okay, you can see the ECAP zone. We have after this we have a ECAP zone and we have a direct extrusion zone. Okay, induced in the die. Okay, so how many deformation zone? 1, 2, 3 deformation zones are there. Okay, this is how we have calculated the theoretical strain. Okay, by using this formula, theoretical strain twist slope. Okay, theoretical strain with ECAP and direct channel and theoretical mate process. Okay, so there are 3 important zones: twist zone, channel only, and corner angle zones. Okay, so we have optimized the die first. Okay, so this see, if you are inducing more and more deformation zones, then the complication of the process, there is a complication in the process, a complication in the material to come out of the deformation zone. So what we did is first we have gone for optimization. Okay, with the several angles, with the trial and error, we have optimized this die. Okay, with several different angles, with varying the beta angle, that is twist slope angle to 40, 45, and 50, channel angle to 90, 100, 110, and outer corner angle 0, 30, and 60 degree. The output parameters is effective strain. How we can get an effective strain and strain inhomogeneity coefficient and the peak punch load, because load is also very important. So more number of deformation zone requires heavy load. Okay, to be induced on the sample to take the sample out. Okay, so these are the challenges we have faced. Okay, so we have optimized the die first, then we have gone and we have developed the numerical, we have undergone various numerical analysis of several dies, and finally we have made a die. Okay, so these are the various FEA conditions we have used. Okay, since we are running out of time, only 5 more minutes, quickly I have to run for this one. Okay, these are the FEA results. Average effective strain we have calculated by using this formula, and strain inhomogeneity, okay, we have calculated using this formula. So analysis of average effective strain, you can see these are the effective strain obtained from the samples. Okay, we have gone for several samples. There is effective strain distribution for slope angle of 100 degree and the corner angle of 0 degree for various twist slope angle. You can see the effective strain achieved. Okay, effective strain. You can see the strain achieved is 4.9. Okay, 4 strain for C, that is beta is 50 degree. For beta angle 50 degree, we have attained an effective strain angle of 4.96 when compared to the effective strain of 4.6 and 4.8. Okay, so then effective strain distribution by taking beta 45 degree and corner angle 30 degree centigrade and keeping the slope angle at 90 and 100 degrees centigrade, we can see the effective strain achieved is 4.6 in this slope angle at 100 degrees centigrade and 90 degrees centigrade. So 90 degrees centigrade gives us more effective strain. Okay, the similar trend is attained for the beta is 45 degree and psi angle. So various several combinations we have obtained. Finally, we have developed a die. Okay, with the strain inhomogeneity also we have see this one. This is the strain inhomogeneity diagram. Effective strain inhomogeneity is the transverse direction of the twist slope when beta 40 degree, beta 45 degree, beta 50 degree. You can see the in 50 degree the intensity of the strain distribution is more when compared to the other 2 degrees. Okay, that is 4.6, 4.8, and 4.9. You can see the strain effective is 4.9 here. Okay, so beta is equal to 50 degree. That is beta is slope angle. 50 degree produces as very good strain homogeneity. So we have selected this parameter. Okay, so you can see this is the strain distribution in the transfer section for the direct channel zone with beta is equal to 45 degree and corner angle at 0 degree centigrade, and beta is 50 degree and corner angle 110 degree centigrade. Sorry, slope angle and twist angle at 110 degree centigrade, keeping the corner angle at 0 and 60 degree centigrade. You can see this in the first diagram, beta at 45 degree centigrade and slope that is corner angle at 0 degree centigrade and slope angle, sorry, twist angle at 90 degree centigrade. You can see the variation in the strain homogeneity is less. The gap between this is, see, you can see this is a lot of the less homogeneity, whereas here you can see the lot of strain homogeneity, that is 2.705. Okay, so whereas here the gap is very less. Similarly, here the gap is less, where the gap is more in this diagram. That is for one psi is equal to 60 degrees centigrade. Okay, so this is the effect of the beta. That is, beta is the slope angle on various channel angle and the corner angles. Okay, you can see in this first diagram, the channel angle at channel angle 90 degree, you can see corner angle 0 degree, at beta 40 degree, you can see the inhomogeneity coefficient is 0.17. Okay, similarly with the channel angle at 90 degree and psi, that is bend angle at 0 and slope angle 45 degree, you can see the strain homogeneity is here. Okay, like this we have developed. Okay, so then similarly we have carried out the effect of peak punch load. Okay, so at the beta is equal to 40 degree. Okay, you can see the peak punch load is 105 and the beta is 45 degree. You can see the peak punch load is 110 and beta is 50 degree. The peak punch load is 120 to 125. So already I told the beta is equal to 50 degree gives us a very good effective. So we have developed the die. Okay, then we have gone for on various optimization process like ANN and GA parameters in order to find out the optimum parameters for the die, to design a die. So you can see with the experiment with the twist slope angle, okay, we can get an optimal solution of 42 degrees centigrade, channel angle of 108 and outer corner angle 49. And the effect with these three parameters, we have got an average effective strain of 2.659. Okay, and strain homogeneity is 0.1029. Okay, and peak punch load, that is lowest peak punch load, we have attained with 92.53. We have conducted confirmation test also. Okay, we have find out the percentage error is very, very minimum. So we have developed the die based on these parameters. We can see the strain effect is 4.5. Okay, with this effective strain distribution by using this optimized parameter. Okay, right. So there is a small video, since running out of time, the execution video, I'm skipping out that one. Okay, right. So we have validated with the FEM model. Okay, and this is the die we have developed. Okay, so actually you can see this is the cross section of the die we have developed, which is patented. Okay, we have made different plungers. Okay, so you can see there's two sets of die. Okay, which is made with the container 2 numbers, split numbers, and 4 numbers. Okay, so this is the hydraulic press where we have conducted the experiments and we have conducted a tensile test and the hardness test of these samples. Okay, so we have took the EBSD results of these samples. We can attain an average grain size of 3.1 micron meter. Okay, so when the material when in the lateral region and the central region, we can obtain a 3.9 micrometer. Almost the homogeneity is obtained by means of this average grain size in both sides. Okay, so you can see this is the lateral region of the extruded copper. You can see the percentage of low angle grain boundaries is 45.6%, whereas the high angle grain boundaries is 55.4. What is low angle grain boundaries, high angle grain boundaries? Low angle grain boundaries means if the grain sizes angle is lesser than 10 degree, it is called as low angle. If the angle is greater than 55.4, it is a high angle grain boundaries. Okay, so you can see the central region of the extruded copper, the high angle grain boundaries is more at the center. Okay, whereas in the low angle grain boundaries are high in compared to high angle grain boundaries at the center of this sample. Okay. So this is the comparison of effective strain and hardness of the process alloys by various novel SPD techniques. You can see with the MECH process, we have obtained an effective strain of 2.7 and the inhomogeneity coefficient of 91.27, which is the current process. Whereas in one process it is superior, that is TCAP, but it was reported that we have to go for more number of passes, even though effective strain is 3 and inhomogeneity coefficient, difference in the hardness percentage is 1 or 2. Okay, in the TC map process, which is developed by Kosic et al. In 2014, but it was reported that the material still has an inhomogeneity and we have to go for more number of passes to attain this TCAP process, but which we have attained almost 2.7, which is dominant over the other process with the MECH process. This is our finding, primary finding. So conclusion is the optimized MECH die geometries using AN and GA, where slope angle of beta 43, channel angle 108 and corner angle 50. So among the selected die geometries, beta has a high influence on strain homogeneity, and on contrary to the ECAP, the strain inhomogeneity was reduced for outer corner angle at 60 degree and it was increased for the larger angle of 120 degree due to MECH process. So the MECH process produced an effective strain of 2.703, which is less strain in homogeneity reduced to punch load in a single pass than existing integrated SPD process, which is a novelty of this process and a novel finding of this process. Okay, right. So we have published a paper which is waiting for the grant, and we have published several papers in International Journal of Material Forming and Metals and Materials International with this work. So these are the references used for the study. Thank you so much. If you have any doubt, you can ask. I'm happy that I have completed within the allotted time. Okay, lot of processes and lot of research findings. So the participants, if you have any doubt, you can ask me now.
Participants can unmute and you can ask queries.
Sir, good evening, sir.
Good evening.
I'm
Yes,
Srinivasan, calling
Yeah.
from Dindikal.
Yeah.
Sir, in all these processes, the deformation is very, very higher. So in that
Yes.
case, what about the ductility?
The ductility will reduce. Definitely the ductility will reduce. Okay, because if the strength of the material increases, the ductility will reduce. Okay. So we have
Even
to
in normal
compromise.
plastic, so even in normal plastic deformation, we need a number of passes, and in between annealing is required for normal forging or any kind of plastic deformation processes. So what about this? In these processes, we are using actually a first pass, a second pass, third pass, like that. You are going for number of passes, but
Yes.
whether we need to go for any in between annealing processes like that, or there is no need for that.
So in between annealing, so prior to processing the sample, if you go for annealing, then there will be it will be easy for you to process the sample, because annealing reduces the strength of the material initially. Okay, the initial sample is subjected to annealing. In between annealing is not needed, but nowadays, in order to improve the ductility of the SPD materials, you can try for aging process. Okay, that's what one finding has told. Okay, you have to go for aging. Okay, you have to go for natural aging, or if you go for artificial aging, so that we are working on that one. This is our next part of our work. Okay, we are planning to do that one. So we have now optimized a die with a MECH process, which includes several deformation zones to reduce the number of passes. Now the prime importance is the ductility, because once the ductility strength, we have concentrated strength and hardness. Now we have to go for the ductility of the material. Okay, so as you correctly pointed out, in order to improve the ductility, we have to go for some aging process. Okay, we are working on that one now.
Sir, one more question, sir.
Yeah,
In roll bonding, we explained actually how the two materials gets bonded. Any frictional heat or is developed, or
no. Already, whenever I explained, I told you. Okay, it is similar to the composite. Okay, we have to add some coupling agent, additives. Okay.
Okay, sir.
In between the surface in order to get it bond. Otherwise, due to only friction alone, it won't stick. Okay. Some additives we have to add.
Okay, sir. But how it becomes homogeneous, sir? But because there is an additive, is there any interface is going to be
additive means you are not going to apply more. Okay, a small light glue. Okay, we are going to apply. Then after that, we are going to press it. Okay, we are going to roll it as several number of passes. Okay. I think it does not have a lot of effort. We have not worked on the ARB process, but it is the finding which I have read from the journal papers. Okay.
Okay. Thank you, sir.
Yeah, thank you. Any more questions?
How the FEA process is carried out by means of linear and non-linear?
It is non-linear process only. Hello.
Sir, one participant asked questions in YouTube chat. What is the recommended size of the hole in the die where the material is passed?
Here we cannot go for that is this SPD process are suitable for only processing prismatic components. Okay, prismatic components, not the circular components. Okay, still there is a lot of difficulty for processing the circular components. Okay, So mostly lot of research work is carried out only the prismatic samples, okay, which consist of length, breadth, and thickness. Okay.
Okay, sir. Thank you.
So next question. What are
Yes.
the different types of hardness tests conducted?
Mostly the Vickers hardnesses, because since it is an ultra fine grain structures, okay, the material is this is a SPD processed samples. Ultra fine grain structures are produced. We go for Vickers normally.
Sir, one more question.
Yeah.
Sir, what about the internal stresses? Because it is going to be a severe plastic deformation. Whether the internal causes any internal cracking like that?
No, we didn't observe any internal process, because that's what we have to be more concerned with the dye manufacturing. Okay, the dye manufacturing. So initially I had experienced the internal cracking. Okay, because of developing a dye without any FEA simulations. Okay, so whenever you are optimizing, if you are simulating the dye. Okay, simulating the component in the dye, okay, you can see, okay, which optimal angle will yield you good result without any cracks. Okay, and also another important concept here is you have to apply some back pressure at the exit. Okay, by giving a plate. Okay, whenever applying the punch, okay, load on the punch. Okay, material starts to deform now. So when the outer end is open, okay, then we cannot induce more pressure. So the back pressure is applied at the end. Okay, by passing a plate. Okay, so that the compressive stress will be acting due to the sides of the die, and the tensile stress will be acting due to the back pressure. Okay, so that material starts to rotate. Okay, after that we have to take the back pressure plate so that the material starts to flow easily.
Okay, sir.
I hope I answered you. All right.
Yes, sir. Yes, sir.
Sir, thank you, sir. I hope you have answered all the questions from the participants.
Okay, thank you so
In
much,
case
sir.
any queries,
Yes.
I will share your mail ID so that they can contact
for
you.
that only I'm going now. So you can share if there are a lot of scope of research in SPD. Okay, so the initial work is very hard. Okay, but once if you achieve, okay, you can publish several papers in this one, because more number of work is not being carried out in India. Okay, on bulk farming, right? So I can say that I am the only person who has carried out the work in made process. Okay, we have developed the dye. Okay, so if you have any doubts in working on SPD techniques, you can just post me a mail to my personal email Iqbal@gmail, or official mail mohammed@srm.edu.in. And thank you very much. And now I'm stopping my sharing, and I think I have given a lot of information, research information to your to the participants. Thank you so much for Dr. Francis. Okay. 1 second, sir.
Thank you so much, sir, for giving us a clear picture about metal forming and the advances in a comprehensive review. And we take pleasure in thanking you for accepting our invitation with a short span, and you have made an excellent presentation to our participants. On behalf of SWarnandhra College of Engineering Management, on behalf of Mechanical Engineering Department, and on behalf of Organizing Committee, I thank you sincerely for your valuable presentation, sir. Thank you very much.
Thank you so much, sir. Thank you.
Thank you. So, dear participants, our second session will start in another 2 minutes. And attendance and feedback link will be shared at the end of the session. So you can check your Zoom chat box, as well as if you are in YouTube, you can check your YouTube chat box. After the questionnaire session, the feedback link will be posted. Arul, Jeyakumar sir. Dr.
Yes,
Arul sir.
Dr. Francis. Yes,
Yes, sir. Good evening, sir. Good evening,
Yeah,
sir.
yeah. Good evening. Good evening. How are you?
Yeah, fine, sir. Thank you.
Yeah.
Sir, now you can share your.
Yeah. You just check. My voice
Yes.
is okay?
Yes, sir. You are audible. You are
Yeah.
audible.
Is the slide visible?
Yes, sir. Yes, sir. This is visible.
Yes, sir. Sir, just a second.
Yeah. Before that, I want to check my video whether it's playing from your side or not. Just a moment. I'll just. The voice is there.
Yes, sir. Yes, sir.
Can you hear the voice? Video voice?
Play, sir. Play it, sir. No, sir.
Can you? No.
Sir, when
Yeah.
you sharing, you share. You can. There's an option, sir, to share the computer audio also.
I'll
You
see to.
stop sharing, and again, when you share screen there, that time the option will come, sir.
Yeah.
Or it's not about
Yes, sir.
the
Yes, sir.
steam
It's
that
audible.
powered our
Okay,
factories in
okay,
the first revolution.
Thank you, sir. Yeah, we can just go.
Sir, so welcome back to you all. And now I'm going to introduce our second session of day one. Guest speaker, Dr. Arul Jeyakumar, Associate Professor, Manufacturing Technology. He is specialized in Material Science, Industrial Engineering, and Industry 4.0. He is professor from SRM University, main campus, Kattankulathur, Chennai. He completed his PhD from Annamalai University with a specialization of biocompatible fiber-reinforced polymer composites. Has having an experience of around 20 years, and his areas of research in biomedical polymer and ceramic composites for hard tissue replacements. And Sir has various awards and achievements. To mention a few, Sir has got a gold medal in PG in engineering design from Anna University, Chennai, and received various prizes in CNC training program projects held in MIT campus, Krompet, Chennai. And Sir has received the Best Teacher Appreciation Award during the year 2010 and 11, and also Outstanding Award and Prize for coordinating and constructing the projects. And Sir is having various memberships like MST, IET, and CSI and SA India. And currently he's working on biomedical-based polymer composites. And Sir has a wider knowledge in the area of material science, industrial engineering, industry 4.2, and manufacturing technology. With this short introduction, I would request our second session, Professor Dr. Arul Jeyakumar sir, to present it. Sir, please.
Yeah. And I thank Dr. Francis for a brief introduction. Actually, I was graduated from Annamalai University in the year 98, and I did my postgraduate in Anna University, and then I did my research in Annamalai, and has been narrated in the material science, that is polymer for the biomedical composite. Actually, my area now, what I am concentrating is the stealth application for the militaries, and the stealth-based materials we have been developing, and in collaboration with the Defense Institute of Advanced Technology, Pune, and a few projects we are running out. And also, since it's always towards the material, because material plays an important role, as Professor Iqbal has described, how the forming can be made with the material, because each material has its own characterization. I want to just highlight the other part of the material, which is manufacturing, because the title itself says the advancement in the material manufacturing and the technology. So all this is clubbed together, and today's we can say like the day topic is Industry 4.0. I hope everyone is audible and clear with my voice. So I'll continue with the slides, and today's before entering into the discussions,
sir.
or the before entering into the further slides discussion, let us, because everyone knows what the world is moving on, and what is the revolution that has been happening in the manufacturing industry, because that is where the outcome or the economy of the country or the GDP and everything is focused towards the manufacturing sector. So though we are working with the materials in lot, and the outcome is so important. The outcome in the sense, the profit that we make and the product that we make should suit the customer's need. So that begins with all principles and design of any product. So Industry 4.0, as we all might be knowing, it is the fourth revolution in the industry, and it is where the cyber physical system has been linked together to march towards the finding of new ideas with all the fields, like starting from the computer, bio mimic, and also towards the other part, like the manufacturing technology. So to start with, it is a cluster, because Industry 4.0 is not an individual thing where we can just speak that it belongs to mechanical field, okay? Because nowhere hereafter we can't hold our own field and work towards the technological growth. So the Industry 4.0 is a cluster or a combination of computer science, the mechatronics, and the other parts of the core engineering like mechanical. So we let us just have a few variety how that the industry revolutions has been taken place. Like in the year 1780s, okay, 1787, in fact, the Industrial Revolution 1, which was established by the invention of water vapor steams, which are being used as a power to run the engine. So that is termed as the Industrial Revolution 1. And then we march towards the Industry 2.0, where the invention of the electrical motors, which are being powered the engine, and that is termed as Industrial Revolution in the year 18th century, that is 1870. And the Industry 3.0 was coined after the intervention of the autonomous and the other CNC, NC machines into the industry or the manufacturing sector. In the year 2000 and 2010, we come to the fourth revolution of the industry, and it is termed as Industry 4.0. And where we use a cyber physical system. It is like connecting the machine with the man, or a man with a system, and how that everything is being linked with the help of data. So we'll be seeing how this Industry 4.0 is working, and many a country are looking towards or marching towards the Industry 5.0. So this Industry 4.0, as I told, one was started, emerged in 1784, and in 1870 we have the Industry 2.0 with a steam engine, and then with the electrical engine, and with the intervention of the automation, computers, and electronics, we march towards the Industry 3.0. Now we are in Industry 4.0, and where we have the IoT networks protocol, and we also have digital manufacturing and artificial intelligence, big data. All these might be a new term for us, but all these are combined and almost into our system. So this Industry 4.0 was coined in the by the BMBF in German in a fair called Hanover MECH Industry Fair in 2011, and it is how the cyber physical system has been evolved for the business model, and thus makes it possible of the shifting into the industrial automation. So the first industrial revolution was held with the power generation, mechanical automation with a steam engine, and that drives the quality of the life of engineering science. And in 1913, with the second revolution of industrialization, where the mobility have been happening with a conveyor belt with the help of the electrical motors. And in 1954, the electronic automation was come into existence with the help of the computers and the numerical controllers and the program logical controllers. We have the electronic systems that terms the third industrial revolution. And in 2015, the smart automation that plays the important role in establishment of the Revolution 4 with the information communications technology. So it is the Industry 4.0 is a cyber physical system where the computation is being physically connected, and it has been controlled by a system using the information or the data that has been gained from the previous or the histories, using the cyber security through a communication system. So Industry 4.0, as I told you, it is not a single system, but it consists of the digital technology, the robotics, artificial intelligence, sensors, big data, 3D printing, software as a service, and cloud computing, IoT, algorithm, value chain, and so on. So the system is all these words are very new. Like, let us start from the IoT, Internet of Things. So this is where we have a different approach of connecting the things from man to man, or a machine to machine, or a man to a machine, using an algorithm, using the data which has been available. So the system of this Industry 4.0 is entirely different from Industry 3.0, which is automation, because many a time we may just have a confusion, what is automation and what is this Industry 4.0 place. So automation or Industry 3 says that it is like, if suppose I want to get up in the morning, and I keep alarm in my clock for 6 o'clock. Okay, what it does, by 6 o'clock tomorrow morning, it will ring and it will wake me up. Okay, this is automation. Normally, what we do in a CNC, we feed the CAD drawing, and this CAD drawing or a code will generate or take part in the manufacturing process, and it will take out the give out the product. But in the Industry 4.0, what will happen is, like the same situation, I want to get up at 6 o'clock tomorrow, and if it is raining, then my bell should ring half an hour before, that is by 5:30, and wake me up. Not only that, before waking me up, it should also switch on my geyser and also my coffee machine. You just understand the situation between the both. The first is automation, where 6 o'clock it rings, and with the sound I just get up. Okay, but the second part is like it should ring if it is not raining. If it is raining, then it should ring half an hour before, so that before I get up, 5 minutes before I get up, the geyser switch should be on and the coffee machine should be on. So this can be done only using the IoT system. Okay, because all we have the smart house, smart factory, smart everything. We are been talking about a smart city. Okay, what is a smart city is everything happens in connection. Okay, everything happens in connection as the situation I have told you. For example, the ringing of bell. Okay, so the same aspect. Okay, here comes the another important factor, what is called as a artificial intelligence. Okay, artificial intelligence is nothing but the machine that mimics the human behavior. Okay, it is very simple. Artificial is the replicate of a small size brain. Okay, we can't compare it with our brain. It is a small size brain, or a replication of our human brain. Okay, that is artificial intelligence. Using this artificial intelligence, because many times industry 4.0 will be very confusing. What is industry 4.0? Why should we go for that? Okay, industry 4.0 will give you a smart factory. Do you know what is a smart factory is? I don't have any operator inside a industry, and my industry will be running in some other remote place where I'll be away from that particular location, and I can run the industry even without a light switched on. Okay, please understand the situation. Such automation, okay, it is more than an automation, like a human who is in front of a machine, how he decides. Okay, for example, in automation or a CNC machine, whatever the material we feed, okay, it will not analyze. Okay, it will execute the particular coding and it will give the product. But in a industry 4.0 mission, okay, or a system, will analyze whether the fed material is what it has to execute or what it has to mission. Okay, all these sense of understanding the feed of the material, nature of the material before it execute the measuring process comes under this particular category of industry 4.0. So this is already in existence in almost all the countries, okay, to the fullest. But we India are marching towards it to a 60 to 65%, and may reach by 2025 70 or 72%. So the next factor, okay, in the same thing, the sensors, okay, because the sensor plays the important role in the physical system, as the name itself denotes, like a cyber physical system, CPS. The physical system is nothing but the cameras, sensors, and other things that takes the actual positions and manipulated it into a data, and filter the unwanted data and send the raw data to the data analyzer. And in the analyzer, it identifies what data has to be compared and what decision has to be taken based on the particular data. Okay, for example, it is a very, very small thing. I'll say you stand before a camera, okay, door locker, automatic door locker. Based on your image scanner, it will open. So what it happens, the sensor or the camera, okay, camera will take the face recognition or capture the face, and the face captured image will be filtered. Okay, because it does not need anything behind us. So all the environmental will be filtered. only the image will be taken to the next stage, and in the next stage, the comparison of your image, which is already stored, will be compared together. And if it is okay, then it will allow the application to work. Application is nothing but the servo motor or the actuators that works. Okay, this is the entire setup or the architecture of IoT. So when we see the building blocks of Industry 4.0, we have the autonomous robot and simulation. Okay, we'll see all these things. Autonomous robot is the robot because all the industries are working with the high-tech robots, and the simulation is the next part, very important, because every time we can't lose our money for training the agent or the robots or training any particular system. So we go for what is called as a digital twin. Okay, digital twins, because many a times you might come across with this word digital twin. Digital twin is nothing but practicing or taking the practicing of training the robots many a times, so we need not lose money in the failure of the robots. So what we do is, by simulation, we analyze what will be the failures occurs in the robots. Such is called as a digital twin. We'll have a message in the coming slides. And the horizontal and vertical system integration. Then comes the Internet of Things with the cyber security, additive manufacturing or digital manufacturing, and augmented reality. Okay, that is so important. AR and big data analytics are the building blocks of Industry 4.0. Let us see a small video to narrate what is this Industry 4.0, how it exists. Can you hear the sound?
The fourth industrial revolution has begun, and you have the chance to be part of it. This isn't going to be like before. It's not about the steam that powered our factories in the first revolution, or the mass production model that dominated the second, or even the emergence of computer-driven systems from the third revolution that we're living in today. Industry 4.0 is about connectivity. It's an opportunity to radically change the way industry responds to the needs of society. As previous industrial revolutions were led by innovations in manufacturing processes and systems, the advancement of Industry 4.0 will be driven by a smart, interconnected, pervasive environment. The opportunities for disruption are huge, and those left behind will feel it acutely. There is still space for leaders of this new revolution to emerge, but the race has already started. Understanding what current leaders are doing will help you join them. KPMG formally examined what those trailblazers were doing in their factories and their offices, and it revealed some thought-provoking findings. Our research highlighted a number of areas that current Industry 4.0 leaders are focusing on. Leaders are planning ahead with clear strategic vision, driven by performance and tying investment to proven opportunities for growth, progress, and innovation. They are focused on discovering how smart products and processes can be developed. Integration is key. The major players are moving away from isolated silo-driven development, which limits scope and value of new projects. Instead, they are moving towards large-scale and proactive integration across their enterprise and among their customers, supply base, and products. To ensure they are aware of every possible opportunity Industry 4.0 technology has to offer. Perhaps most importantly, they are not afraid to think big and act bold. This means nurturing innovation, developing disruptive thought processes aimed at devastating the status quo, and looking for opportunity in every element of their value chain, from which products are designed and how they are produced, to who they are sold to and how they are purchased. Your organization may be radically different in the future, with a range of products, services, and processes you can't currently predict. Do you want to join the leaders of Industry 4.0? Can you afford not to? Then our advice is, plan ahead. Fight radical change with integrated radical action. And embrace the fact that it's time for manufacturers to step up and start making smart, bold moves. If you don't, you could be left behind.
So this is what the Industry 4.0 is speaking about, because already there is a development of particular thing. Okay, like we'll just go across with the topics and we'll analyze why this Industry 4.0 is highly necessary and what will be the future factory and future world. So when you say the big data, okay, let us start from the big data. Already IoT is nothing but the connecting of the things, okay, with the physical thing. For example, if it is industry, I connect a CNC machine with the particular software, and the software is indirect connected with the system, okay, robotic system. So whatever it needs, for example, if the raw material is feeding is required, it will call for the raw material feed. And if the material is not the one which is assigned for the operation, then immediately there will be a checklist and or denial of the operation will be indicated, and the change of the particular raw material will be done. So the big data, because the big data is another concept. It is the storage place where the nominal data of any requirement. For example, I am into manufacturing of a product, say like a gear. Okay, this gear specifications or the calculations of the teeth based on the pitch circle. All these data are the data what is required for the calculation, and other things will be there in the big data. And this big data is being maintained by big servers like the Wikipedia, the Google, and the other people, where they have these data in their hands, and whenever it is required for the manufacturing unit, or for any, for example, if I want to search a location in my Google map, immediately I get the information. Where I get it is from the big data, where it is already been stored. And likewise, the data that is required for this Industry 4.0 manufacturing or the calculations can be obtained from this big data. So when the physical data are being taken, and these physical data are being analyzed, and during analyzation it requires some data from the standard data or the earlier data that can be obtained from a big data. And using a AI concept, this training will be happening, and the execution of the particular manufacturing will be executed. So like IoT applications, we can see a smart factory where the factory runs without operator. That is what we told. And connected marketing, innovation, reducing time to market, connected gaming, micro payment, and also smart grid, connected supply chain, new work style, physical cyber security, business process outsourcing. So the layers, as I told you, the IoT has 7 layers. The physical layer is the first, and then goes with the fog or the edge computing. Then the data ingestion and data analysis, application, and then the output. So the first 3 layers are called as operational technology, and the remaining, the data processing and the application layer, are termed as information technology. So the big data, as we see, the AI concept, AI is a replication or the mimic of a human brain. So it takes place in the first phase, that is the physical capture of the images or taking the inputs, and also in the edge computing or a fog computing, nothing but filtering out what is not required and taking it as a data source for the next level of analyzing. So everywhere in the data ingestion, we need a lot of information out of the other things to manipulate the data that has been observed and sent by the particular edge computing through a network protocol. So here comes the AI, which will take a decision based on the concept and the data analysis to execute its process using the application or the end user. So the other 9 pillars of Industry 4.0 starts with simulation, that is the digital twin, and system integration, that is the horizontal and the vertical integration. Okay, that is called as a decentralization, taking any decision on spot with respect to the environment, and the Internet of Things as a connection between the physical and the human. And next is the cyber security, because the cyber security should be a part of this, because every time, even in the industry, physical industry, we may worry about losing of data, but this cyber security ensures and takes the industry revolution to the next level. And cloud computing plays another important role. Cloud computing is nothing but the server. Okay, the server owned by the other people, and the major cloud providers are Amazon and Microsoft, Google, and other people. So what they do is they give their server for our purpose. So server means for the storage purpose, and they lend the softwares for rental purpose, and also the other platforms for the rental purpose. It is very simple that if suppose I want to work with a particular software which cost about 15 lakhs per user, okay, then I can't afford to pay for it and work it for my business. What I have to do, what I can do is I can take the service from the cloud providers, and whatever I'm using for the period I'm using, I will be paying for them. So such facilities also are required in this particular concept of Industry 4.0. And then comes the additive manufacturing. We also call it as a digital manufacturing or a 3D printing, and then augmented reality, because augmented reality is one of the boon in the Industry 4.0. It will give you the actual picture of the product before it has come into existence or physical appearance. Then comes the big data, which will be highly helpful for the manipulation, and also with the help of the autonomous robot, we need it is highly required to build the Industry 4.0. So all these nine concepts or the things are called as a pillars of Industry 4.0, starting from digital twin or simulation, system integration, IoT, cyber security, cloud computing, additive manufacturing, augmented reality, big data, and autonomous robot. So the IoT is a physical things in Industry 4.0, where the devices, machinery, robots, systems, equipments, sensors, and the camera or any other real-time things are being providing a real-time data about their performance, condition, or location. So for which, based on these data, it will be taking the decision and making the execution. The big data and analytics, it is the second concept where already been discussed. Like it gives the required information or the data to take a decision or to take data to the next level of understanding. The cyber security is so important, as many people we worry about the losing of data, which is ensured by the cyber security, and it has developed to a greater extent where there is a less threats from the cyber world. Next is the cloud computing. Cloud computing is a great enabler of digital transformation. The present scenario, the cloud technology provides enough, it is unscalable and interoperable, because those things are very important, because the IoT concept is interoperable. Okay, that is because if I am working with my computer, it should also be, my concept should also be visible and executable in the next system. So that concept is there in the Industry 4.0. And additive manufacturing, like the organization have begun to adopt additive manufacturing such as 3D printing, mostly to produce individual components and prototype. And the horizontal and vertical system integration is where we take a link of all the things and for taking the decision then and there. Autonomous robot, it plays an important role in the particular execution of the Industry 4.0 activities. And digital twin and augmented realities are the pillars. So the data in IoT as a big data or the other, which has been stored in the terms of metadata, and there is almost every day there is a lot of data are being stored in this part where it can be recovered or we can use it in the particular system. So artificial intelligence is a machine that mimics the human behavior. Likewise, machine learning, okay, it is a subdivision in artificial intelligence, subset of AI, to ensure the machines to improve its experience by statistical method. And deep learning is again a subset of machine learning, which makes the computation of a multi-layer neural network feasible. So the 6 design principles are interoperable. I told you the system or the ability of the physical cyber physical system to connect to any system by communication or through the internet protocol is the interoperability. And visualization, because that is again an important thing where we have seen in the 9 pillars, that is the augmented reality. So it is the ability of the physical cyber physical system within a smart factory to make a decision of their own, and in the decentralization process. And real-time capability, the capability to collect and analyze the data and provide the insight immediately. And likewise, the service orientation, offering of the service via the internet, that is so important. And modularity is the flexibility of changing the manufacturing things as and when required. So we'll see.
The Internet of Things, or IoT, is influencing our life.
Sorry. We'll see about the Internet of Things, how it works, and what is the necessary in this Industry 4.0.
The Internet of Things, or IoT, is influencing our lifestyle from the way we react to the way we behave. From air conditioners that you can control with your smartphone, to smart cars providing the shortest route, or your smartwatch which is tracking your daily activities. IoT is a giant network of connected devices. These devices gather and share data about how they are used and the environment in which they are operated. It's all done using sensors. Sensors are embedded in every physical device. It can be your mobile phone, electrical appliances, vehicles, barcode sensors, traffic lights, and almost everything that you come across in day-to-day life. These sensors continuously emit data about the working state of the devices. But the important question is, how do they share this huge amount of data, and how do we put this data to our benefit? IoT provides a common platform for all these devices to dump their data, and a common language for all the devices to communicate with each other. Data is emitted from various sensors and sent to IoT platforms securely. IoT platform integrates the collected data from various sources. Further analytics is performed on the data, and valuable information is extracted as per requirement. Finally, the result is shared with other devices for better user experience, automation, and improving efficiencies. Let us look at a scenario where IoT is doing wonders. In an AC manufacturing industry, both the manufacturing machine and the belt have sensors attached. They continuously send data regarding the machine health and the production specifics to the manufacturer to identify issues beforehand. A barcode is attached to each product before leaving the belt. It contains the product code, manufacturer details, special instructions, etc. The manufacturer uses this data to identify where the product was distributed and track the retailer's inventory. Hence, the manufacturer can make the product running out of stock available. Next, these products are packed and parceled to different retailers. Each retailer has a barcode reader to track the products coming from different manufacturers, manage inventory, check special instructions, and many more. The compressor of air conditioner has an embedded sensor that emits data regarding its health and temperature. This data is analyzed continuously, allowing the customer care to contact you for the repair work in time. This is just one of the million scenarios. We have smart appliances, smart cars, smart homes, smart cities, where IoT is redefining our lifestyle and transforming the way we interact with technologies. The future of IoT industry is huge. Business Insider Intelligence estimates that 24 billion IoT devices will be installed by 2020, and IDC predicts that.
So this is the IoT, where it links with, for example, a product has been manufactured, and the total history of the product will be there till from the production starting till it has been the end cycle life of that life cycle of that particular product. So the potential implications are like a robot of this industry 4.0 is a robot assisted production and predictive maintenance and additive manufacturing, machines as a service, and big data drive quality control, production line simulation, and smart supply network. So the impact of industry 4.0, as already told, the economy of particular industry or the country, the business, national and global development, and the society, and for the development of the individuals. So let us see some of the industry 4.0 in the Indian railways, like smart coaches, smart yard, star depots, and production unit. Like most of the governance of this Indian railways are being carried by the industry 4.0, where the execution and line changes are been happening as per the industry 4.0 network connectivity. So the future factory will be like this, without any mission. The people standing over with the discussion, and they can operate an industry in a remote. So this will be happening, and it has been there with the industry 4.0 in a fullest manner. So when we talk about the digital manufacturing, because that is so important and it is a part of industry 4.0, like the internet, intranet, and extranet, and also the digital model and the information models are required for the development. And digital manufacturing is nothing but a smart manufacturing, where the in earlier stage, when a car has been manufactured, we have n number of parts where it has been produced separately and it has been assembled. But after this digital manufacturing or the 3D printing, all the most of the parts have been combined, and the work of manufacturing or the parts in a particular products are being reduced. So there is a lot of changes, like the traditional factories. We need to work, we need to monitor everything, we need to see and maintain. But in this industry 4.0, we need everything will be informed, and it will be rectified by itself, or the further production will not be happen, so that the production or the wastage will be reduced, and also the production cost will be less, so that the product cost will be very less. So the benefits of Industry 4.0 is like helping helps keeping the production in India, and keeps the Indian companies to compete successfully, and bringing leadership to the world markets. Need skilled workers, and gives employment, speed up the production setup process, and knowledge-based high-tech approach, and reduces the complexity. So the opportunities of Industry 4.0, as I was been saying, that there will be no operators or engineers inside the industry. It is not the way that we need to worry for it, because the other opportunities like AI concept of handling the system, and the other process which is involved in the Industry 4.0 gives a lot of opportunities and business for the engineers. So what is a smart factory is concerned? It is the integration of data with the process expertise to enable the evidence-based management of manufacturing a product. So the 6 elements of the smart factories, like flexible manufacturing, automation, robotics, and CAD/CAM, concurrent engineering, and computer integrated manufacturing. So this this is a small clipping.
In this video, we're going to explain what digital manufacturing is. To start with, what is manufacturing? Manufacturing is making things on a large scale, like in a factory. Factories started over 100 years ago. Before that, things were made mainly by hand. A good example of this is building cars. When the car was invented, it was built slowly, part by part. But then Henry Ford came along and worked out how to build cars more quickly and easily, using a production line. Production lines and factories have changed to include digital technology, things like robot arms, which now help build cars. In the future, manufacturing will use more and more of these digital technologies. What is digital manufacturing then? Digital manufacturing is when computers are used to help with manufacturing. For instance, humans and robots working closely together, computers testing things out before you have to try them in the real world, saving time and money. This is called the digital twin idea. Imagine your machine has a twin made from data that lives inside a computer. Whenever you're wondering what something might be like, you could test it on the twin first. So, you're wondering what would happen if you speed up a machine. You could try it on the digital twin. If things go wrong, like a part of the machine gets too hot, you know not to do that in real life. To take this a step further, there's an idea called the digit brain. In real life, we learn from the things that happen to us. For instance, playing with building blocks tells us that a tower needs a good base, or it might fall over. We learn and hopefully remember so we won't make that mistake again. Digit brain tries to do this too. If it is part of a robot, which is manufacturing an object, and something goes wrong, it learns what was happening at that time. What kind of material was it using? What else was happening? It takes this information and learns that there may be a problem if things are the same in the future. It remembers so it can try not to make that same mistake again. How do we communicate with the systems and robots in manufacturing? Should we press buttons? Can we tell them what to do?
Come here, robot.
How quickly should the robots work? How will the robots know what we are doing? When humans work side by side with robots, how they behave is important to us. If the robot moves too slowly, the human could get frustrated waiting around for it. If it moves too quickly, the human might get in the way. The robot may have extra strength to help the humans, but this strength, or force, needs to be managed carefully to make sure the humans are safe. But how do the robots know what the humans working next to them are doing? When humans and robots work next to each other, they both need to know what the other is doing. Humans watch and listen to the robots to find out more. Robots can use things like cameras to see, and more advanced things like heart rate and breathing sensors.
So with this, I hope it's a long subject to discuss on, but with this 1 hour, I have given the concept of this Industry 4.0. So basically, this Industry 4.0 is the next level of making the manufacturing sector, and how that the world will look in future, because as already been told that the machines are going to work by itself, not without the intervention of the human, but not near to them, but from a little distance from the particular machines. Hope I have given enough light on the topic Industry 4.0. Thank you.
So, thank you, sir. Participants, if you have any queries, you can unmute and you can ask. Participants. So thank you, sir.
Okay. Thank you, Dr. Francis, and all who have joined in this presentation. Thank you.
So thank you very much, sir, for your impactful insight on Industry 4.0. On behalf of SWarnandhra College of Engineering, Management, and Department of Mechanical Engineering, and on behalf of Organizing Committee, I take my sincere thanks for the today's second session speaker, Dr. Arul Jeyakumar, sir. In spite of very short span, you have agreed and you have presented, and thank you for your wonderful time, sir. Thank you.
Thank you, sir. Thank you.
So, dear participants, feedback and attendance links are posted in the chat box of YouTube as well as in the Zoom chat. So kindly fill